Okay, now it seems we're live on YouTube, so I think we will get started. So it's my great pleasure to welcome Mijung, and very good morning to you. And I don't know everyone else is who's tuning in. So a good day to everyone else. And it's my great pleasure to introduce Mijung, and she obtained her PhD at the University of Austin under the supervision of Jonathan Pillow, who's now at Princeton, and she developed Bayesian methods for neurocoding during her PhD. And then she did her first postdoc with Manish Sahani at the Gatsby unit in London at University College, focusing on probabilistic nonlinear dimensionality reduction and approximate Bayesian computation. And then I think when she moved to Amsterdam to Max Welling's group, she then started working on privacy, as far as I understood, and is now working a lot on privacy preserving machine learning. And now she's in Tübingen, as some of you who already tuned in heard from our discussion, where she's a Cyber Valley group leader and which is co-located at the Max Planck Institute for Intelligent Systems and the University of Tübingen in Germany. And now she's a group leader there, and so she her entire working group focuses on problems that intersect privacy, but also neural networks compression and interpretability. So kind of this triangle of very important problems, I think. And we're looking forward to a talk on ABC, DP, approximate Bayesian computation, and differential privacy.
Thank you. Now, I guess I will share my screen.
Yes.
Okay. Okay.
And I guess before you get started, I should remind the audience that feel free to use the Q&A feature in Zoom to ask questions and upvote other people's questions, and then we can go through them after the talk.
Okay, so I don't need to think about these questions during the talk. Okay.
No, we'll do them afterwards. I think that's easier.
Okay. So today I will talk about ABCDP. This is joint work with Witawat Sikritum, who works at Google Research, and also my student Margarita Vina-Rose, who works at MPI IAS. So let's imagine you are Bayesian, and unfortunately, the model you consider is a complicated simulator. Something looks like this. Okay. So in this case, given a data set Y star, that has a lot of observations, evaluating the likelihood P of Y star given some parameter value theta is often intractable. But you are Bayesian, so you still want to do the posterior inference. But in this case, since you cannot evaluate the likelihood of your data, even MLE, maximum likelihood to estimate, obtaining this is challenging. But you have a simulator, so you can input some parameter values to the simulator, and you can simulate some pseudo data. Using this aspect, Bayesians don't give up. So what we can do is the following. So we draw some samples of parameters from the prior distribution. In this case, I showed the uniform distribution. And we have some samples and samples of the parameters. And then we input these parameter values to the simulator, and then we get pseudo data, looks like this, for each theta. And now we look at our observation. Okay, that looks like this. And maybe we can choose some summary statistic that explains how that observed data looks. And then we compare these simulated data and the observed data in terms of a certain similarity metric, and also the summary statistic evaluated on these data sets. And if the distance between these two, pseudo data and also observed data, is less than some threshold called epsilon ABC, Then we take these samples and treat them as posterior samples. This is quite sensible, right? In fact, there is an algorithm called Rejection Abc using this sampling and also simulator to do this Bayesian inference approximately. In Rejection Abc, we repeat the following steps for t equals 1 to the larger t, where in each t, we sample the parameter theta t from the prior, and then we sample a data set yt, given the simulator, right? Given the value of theta t we just drew. And then we compute the distance between these two data sets, the real data set and also pseudo data set at each time t. If the distance is less than epsilon abc, the threshold we set, then we output the binary indicator tau t 1, meaning that we keep that corresponding theta t as posterior sample. If not, then we output tau t 0, meaning that we will reject the corresponding sample theta t. And we repeat this until we have C number of posterior samples. So this distance rho can be, for instance, L2 distance on summary statistics evaluated on each data set, right? So let's look at this a little bit. So the data appeared here, and this is nothing but aggregated individual data points. And it is known that in privacy literature, publishing these kind of aggregated statistics isn't safe, because an adversary could have a prior knowledge on this data set, or it is possible to combine some public data set to identify who was in this data set. So there is this could lead to, publishing this could lead to the privacy threat. And in fact, Johnson and Shmatikov in 2013 showed that statistics published as a result of genome-wide association studies can be used to identify individuals that participated in the study. So you might have a vague idea that, okay, maybe it seems necessary to privatize summary statistics, but privatize in what sense? So here comes differential privacy. This is the notion of privacy we will use. How many of you know about differential privacy? Can you raise your hand? And Matthias, can you perhaps tell me how many people know? Percentage? Matthias is not here. Okay.
No, I'm here. I'm just waiting for people to respond. Give them a second. Okay, so there's a little less than half have raised their hand.
Ah, okay. So then I will probably go slow, a little bit slow. Okay.
People have also lowered their hand again. Okay.
Okay, so I will go slow here because this might be new to many people. Differential privacy in plain English says it's statistical science that try to learn as much as about a group, the whole group, but you at the same time you want to learn as little as possible about any individual in the group. Okay, and I will explain this a little bit more in this cartoon. So suppose there is a data set T1, and that contains a lot of people's data. Here I map each person to each data point. So you can imagine some medical data set where each row of the database contains each person's medical history, right? Something like that. And then given D1, we run some randomized algorithm A, and then this is the output that A produces. And in data set D2, now we have the exact same number of people as D1, and they are the same people and same data set, same data points. But now we replace Alice's data with Bob's data. So there is one entry difference between D1 and D2. This is what we call neighboring data sets. And given D2, we run the randomized algorithm A again. And what we hope to get is something similar to the previous output. Why? Because by looking at these two outputs, you cannot distinguish whether Alice was in the data set or Bob was in the data set. So this is a precise idea that differential privacy is exploiting. In more rigorous terms, so they look at this kind of variable called the privacy loss. Privacy loss is probability ratio, log probability ratio between two probabilities, where the first probability is the probability that algorithm A, given dataset D1, outputting a certain output O. And then the second probability is the probability of the algorithm A, given neighboring dataset D2, outputting this exact same output. And what it says is basically, it tells us how well we can distinguish between the two data sets, right? So if we change one data point and there's a large probability difference here, then we will be able to distinguish that difference easier. And using this variable, we define the algorithm being epsilon dp if the privacy loss is bounded by epsilon. And this bound should hold for all possible outputs of algorithm A. So all possible values of O, and also all possible pairs of data sets. So this is when we call the algorithm is epsilon dp. Okay, I hope this is clear. So how do we then achieve such a bound? Well, we can add some randomness to induce such a bound. Randomness to the output of the algorithm, typically. And how much noise do we have to add? Well, the noise variance has to be proportional to these values, and I will go into this. So the first one is called the sensitivity. Sensitivity of an algorithm is the maximum difference you can get in the output of the algorithm given two neighboring data sets. So this maximum is over all pairs of data sets. And if you can think of an algorithm that's very sensitive to any data points change, right? Then to compensate for that difference, you have to add a lot of noise. So this is kind of intuitive. And then the second variable is called privacy loss, that we looked at before. So if you allow for the large privacy loss, then you don't need to add so much noise, and vice versa. So because we are adding noise, there's an inevitable privacy accuracy trade-off here. And we will study this trade-off under the proposed algorithm we present here. Okay, there's an important property of differential privacy that's very much relevant to our talk, which is composability. Suppose there is a sensitive data set, and there are two algorithms. We are running two algorithms given these data sets. One guarantees epsilon 1 dp, and the other one guarantees epsilon 2 dp. Then the union of these two outputs of these algorithms is epsilon 1 plus epsilon 2 dp. So this composability, this particular composability is called linear composability. But what it says is basically the more you access the data, the worse your privacy loss gets. And of course, there are more refined composition methods than the linear composition method. For instance, moments account by AABI et al. But what's important to remember here is that differential privacy has this property called the composability, which brings us a challenge when we apply DP to machine learning algorithms, because a lot of them are iterative, meaning that they access data many, many times. Okay. So now let's go back to ABC. Well, a naive application of DP to ABC could be identifying where the data appears and then privatize that part, right? So where do we see noise? Where do we see data here? So that's where we compute the distance between the pseudo data and the observed data. And we compute this in every T. So what happened is, if we decide to do this, adding noise to the distance in every ABC step, then due to the composability property of DP, this will incur a lot of privacy loss. So this is not an ideal case. I mean, what happened is the total privacy loss, epsilon total, will be proportional to T, the large T, how many times we run this algorithm, where the thing that we actually care is C number of outputs, right? And when we keep those samples. And the problem with this is we are paying privacy budget even for the samples that we reject. So this seems a little bit not efficient. And the idea is that perhaps we could achieve total privacy loss proportional to C, where C is often a lot smaller than large T. Can we achieve this? The answer is yes. Otherwise, I wouldn't talk about this, right? So the answer is yes. And then how do we do that? By making use of sparse vector technique. Sparse vector technique was proposed by Dwork et al. In 2009. And since then, there were so many variants of this algorithm because, as you can see, you can reduce the privacy loss from large T to C. So this is very practical. And there are multiple steps we do in this sparse vector techniques. And let's go over this each one by one. And we repeat these steps for C until we get C number of ones. And the first step is, so here large T is the threshold. Sorry for the confusion, but in sparse vector technique, they use threshold T and they add noise drawn from Laplace distribution, zero mean Laplace distribution with scale parameter B. And the T hat is the noise up threshold. And for each query I, query means we evaluate some function f on the data D, and we do that in every step I. So we also add noise to this query function by drawing sample nu I from the Laplace distribution with scale parameter 2b. Yeah. And then if this noisy distance is larger than the noisy threshold, we output 1. The answer is 1. If not, the answer is 0. And thanks to their smart proof of their technique, the privacy loss only occurs when the answer is positive. And so the total privacy loss is proportional to C and inversely proportional to B, the noisy scale. And here really how many times we ask this question to this database is independent of the privacy loss we get in the end. So we will use this sparse vector technique and apply this to ABC problem. And here is our proposed algorithm. What we require for running this algorithm is observed data set Y star and number of posterior samples we want to take C, the privacy tolerance epsilon total, this privacy loss that we allow for, and ABC threshold epsilon ABC distance rho. And what's different from traditional ABC to this is basically, we also assume that there are parameter pseudo data pairs, theta T and YT for T equals 1 to large T. This is also available. This is in fact privacy, not related to privacy at all, because you can plug in any values to a simulator and then you can simulate the data, right? So we assume that these are already done by some person and it can be available for anybody, including our adversary. And then we assume we also need some option for resample. This determines whether we want to resample the noise for the threshold, and which will be clear in the algorithm. And what we output in this algorithm is that we output the epsilon dp indicators tau t tilde for all t1 to large T, or until we get the C number of samples for corresponding samples theta T. So in our algorithm, we first calculate the noise scale B by theorem 4.1, which we will go into that later. Let's assume for now, there is a noisy scale B that's given. And then using this noisy scale, we first privatize the ABC threshold by drawing some sample from the Laplace distribution with scale B, which we will call MT. Okay, so now we add MT to the epsilon ABC threshold, and then we get epsilon hat ABC, and we set count 0. And for T equals 1 to larger T, we privatize the distance. Remember, we compute the distance at every time T, and then we add noise also in every time T. That's drawn from Laplace distribution with noisy scale 2 times B. Okay, and if the noisy distance is smaller than the threshold, noisy threshold, this is also different from the SVT, where they talked about above the threshold, but we are talking about below the threshold. Then we output tau tilde 1, meaning that we accept this corresponding sample, and we update the count. And if the resample is true, then we redraw noise for the threshold. If not, we don't do that. And if the noisy distance is larger than the noisy threshold, then we output tau tilde 0. And we repeat this until the count is larger than C. So we stop until we get the C number of accepted samples. They're indicators. Okay. So now let's look at theorem 4.1. This is a result of the SVT privacy analysis. Basically, what it says is my total privacy loss, epsilon total, is proportional to the privacy loss that's happening only when I have a non-negative, only when I have positive answers. And if I set resample to false, then it's going to be proportional to C plus 1. And the other part is called sensitivity, right? Sensitivity of the distance. This usually scales with 1 over n. So the larger data size typically gives us a smaller sensitivity of the distance. And it's inversely proportional to the noisy scale. And if we set the resample true, then the total epsilon is bigger, right? 2 times C, because we add noise to, we redraw the noise for the threshold as well as the distance. Okay. Okay, here's the algorithm. So we can run it, and then now what, right? So now in the user case, differential private algorithm is established. Then what we want to know is, okay, how does it perform not only on the data set, but theoretically, how does it perform as a trade-off between the privacy and accuracy? So we want to analyze this aspect. And we do that by looking at 2 different quantities. The first quantity we look at is flip probability. In this proposition, we formally state this. Let's first denote the output of ABCDP algorithm at time t by tau tilde. And the tau tilde is a binary indicator, so it can be either 0 and 1. And then we also denote ABCs, the traditional ABCs output at time t by tau t. There's no tilde. So this is also a binary indicator, so it can be taken, this can take either 0 and 1. And the flip probability is the probability that the outputs of ABCDP and ABC differ given the output of ABC. So this is precisely written here. The probability of tau tilde not equal to tau t given tau t. It's some function. It can be written in terms of some function GB, where B is the parameter, and the input argument is the absolute difference between the distance at time t and the epsilon ABC, the threshold we choose. And what is GB? GB is defined here. We can define GB by defining a new random variable, Z, that's by subtracting the noise variables, right? One MT that's added to the threshold, new T added to the distance. And we define Z and then compute the PDF of this Z. And then the GB of A, yeah, this function is defined by the integer of that PDF of Z from A to infinity. So this might sound a little bit vague. Oh, what does it mean? So I can give you some illustration of GB. This is the input argument. Yeah, x-axis shows the input argument of GB, and y-axis shows the function GB. We are talking about binary indicators, so the flip probability can go from 0 to 0.5. And we show this GB at different B values. So the B equals 1 is in this blue trace. B equals 4 is in this green trace. And at any given input argument A, what happens is this flip probability is smaller if B is smaller, right? So B smaller is better, but B depends on many things. So to try to understand this flip probability a little bit more, I made this simulation. Okay, now I will look at the flip probability as a function of total epsilon, yeah, the total privacy loss of ABCDP at a different data size and n equals 10, n equals 100, and n equals 1000. But here I fixed C equal to 10. So we will only run ABCDP algorithm until we get 10 posterior samples. One thing you might notice is that, okay, as we increase the total epsilon, the flip probability goes down, right? Generally goes down and down. But if we have a large data size, the flip probability goes down faster. So for small c, when c equals 10, and small data size maybe in the middle, works okay, yeah, with epsilon around 5, where you can get a small probability, flip probability. And I do the same, but now I make the C equals 1000. So now I compose a lot more, meaning that I will have a lot higher noise variance than before, than when the C equals 10. So now you can notice that even if I increase the epsilon, total epsilon, my flip probability will go down a lot slower than before. Yeah. So in this case, for large C, 1000, only large data set, in this case here, right, works okay with maybe epsilon larger than 50, because that's when we can get small flip probability. So all of these try to say the following. The flip probability can provide a guideline for choosing C, the number of accepted samples, given the data size n and a desired privacy level epsilon total. In other words, suppose I have a data set, privacy sensitive data set, and so n is kind of fixed, right? So I cannot change n. And then before I run ABCDP algorithm, I have to tune C and epsilon total. And if I have a very small data size, then I wouldn't expect to have a good privacy loss if I choose C to be very large, and vice versa, right? So it gives us a way to choose C or adjust your privacy level epsilon total if you want to go for the large C. Well, this was useful, but this flip probability considers only a single output of ABCDP. And I want to have a more holistic view of this algorithm. So now we consider the whole sequence of outputs of ABCDP by looking at the convergence of the posterior expectation. Before we go into that, I will introduce some notation here. So we assume that the larger T, how many times we run this ABCDP algorithm, is fixed for ABCDP and ABC, but the total number of ones can differ. And this total number of ones itself is a random variable in this case, right? So in ABCDP, I call this total number of ones by C, and in ABC, I call this by C prime. And then we look at the following error. This is expected error, the expectation over the privatized indicators from tau t1 to large T. And the error is defined by the posterior expectation. So the first term is given by the samples of ABCDP, because you see this tau t tilde. And then the other term is the posterior expectation computed on the ABC samples, right? And now this expected error is bounded by this. Okay, so what is KT? So KT is basically the L2 maximum L2 norm of the function, arbitrary function we consider here. And then what's interesting is that this error is bounded by the sum of flip probability that we saw before, the GB guy, right? And as we noticed in the cartoon of GB, as we decrease B, the flip probability went down and down. So one thing we have to notice is that this B is also proportional to 1/n. It scales with 1/n because the sensitivity of the distance usually goes down like that. And in our paper, we consider the particular distance called MMD, which gives us an exact 1/n factor. But you can also use different type of distances. And in this analysis, we also assume MMD distance, and also in that case, the sensitivity goes with 1/n, and because of that, the noise scale also scales with 1/n. That means as we increase n, GB will decrease for the same input argument, right? And then when n goes to infinity, your sensitivity goes to 0. So the error goes to 0 as well. Okay. And then we also analyze the probabilistic bound on this expected error. So for any a larger than 0, the probability that this error we saw is less than that constant a is larger than 1 minus this term. This again decays exponentially in n because the noise scale goes with this 1/n factor. And our proof relies on establishing the upper bound on the error as a function of the total number of flips, basically sum of the absolute difference between the output of ABCDP and output of ABC, which in fact is a random variable itself. This actually made this proof hard and challenging. So we ended up using Markov inequality to establish this tail bound. And you can see the detail of our proof in our archive paper. So I hope that we could improve this error bound a bit more. But using this more sophisticated inequalities was not straightforward because of this term itself is a random variable. But if you have a better idea, contact me and perhaps we could improve the bound. And then I will talk about experiments. So in our paper, we did 3 experiments, but I will talk about only one here. Okay, so here, the simulator we consider is stochastic birth-death model. Lintusari et al. Used this model to model tuberculosis outbreak. And this model takes these 4 parameters as inputs, where beta is burden rate, T1 is transmission rate, and R1 and R2 are reproductive numbers. And given these values of parameters, this model simulator produces pseudo data. And as before, the goal is to identify approximate posterior distribution over these parameters given the real data. So I used, so there was no real data, so I used, I generated the real data by assuming certain value of parameters as ground truth, and then did this ABCDP test. in the following sense. Okay, so now let's first look at the samples of each parameters drawn from the prior. And here the vertical black line show the true ground truth values I use for generating the data set Y star, and red vertical lines show the average mean of these samples. Okay, and then I first generated 100 samples for Y star. So now data size is n equals 100. And I ran ABCDP algorithm with resampling option on, true, and without resampling option. And here you can see, okay, our face is here. Okay, I'll move this. Here you can see that the error with resampling is higher than the error without resampling. This is because, as we saw in theorem 4.1, the noise scale is proportional to 2C, 2 times C, if we resample the noise for the threshold. If we don't, then the noise scale scales with C. So it is natural that you get a smaller error. And here we show this histogram of the 10 selected posterior samples. And I did the same thing. Now I increased the data set. So the data set has 1,000 data points. And I computed, I ran ABCDP algorithm with resampling option and without resampling option. And now you can see that the error went down even further because now we have a larger data set and the sensitivity goes down. And that means the noise scale also goes down. And visually, you can also see the different distance between the black bar and the red bar is a lot smaller here than when we had the smaller data sets. Okay. Now we came to the conclusion. So in this talk, I presented this ABCDP algorithm that outputs binary indicators that are differentially private. And we make use of the privacy analysis of sparse vector technique to significantly reduce the privacy loss from large T to C, where C is typically a lot smaller than large T. Well, this depends on your simulator and also the threshold, the epsilon ABC threshold you choose. But typically we keep epsilon threshold small so that your accepted samples are accurate. That usually gives us this kind of a condition, C being a lot smaller than T. And we studied privacy accuracy trade-off our algorithm in terms of 2 different quantities, flip probability and also the error on the posterior expectation. Yeah, thank you for your attention.
Perfect. Thank you very much. That was a very interesting talk about two very interesting topics combined. So I encourage the audience to ask questions. So we already have 2 questions on the Q&A. One was about the distances that you mentioned during the talk, and I think you already alluded to that you've been using MMD, but Mayank asks what other options would be available, and he's speculating about Euclidean or other distances in this case.
Okay, so yeah, our analysis follows MMD because it's easier to compute the sensitivity and so on. But the TB data experiment I did was actually not using MMD. So this Lintusari et al. 2019 paper used a certain summary statistics, and they computed L2 distance of the summary statistics given pseudo data and true real data. But the problem is in that case, there's no bounded sensitivity, meaning that when you change one data point, it's not clear how much difference you will get in this summary statistics. So in that case, what you can do is you can impose a some sort of a hard upper bound on the distance. so in your code, basically you choose either that distance or the largest value you can get in the distance. This is a common trick we use in deep learning and differential privacy, where you don't know how to compute the sensitivity and you impose a certain upper bound that, for instance, the gradient can have, and then you tune the noise variance accordingly.
Okay, that makes sense. Then Lorenzo asks, or he says, thank you for a very nice talk. And he asks whether you can actually adapt your approach to kind of more advanced ABC algorithms, such as SMC ABC, or kind of other variants that kind of go beyond just doing kind of a bit, I guess naive is probably too strong a word, but very simple rejection sampling.
Yeah, that's true. I mean, so for instance, so I guess we can treat these other variants as a soft ABC, where probably you don't output binary indicators, but maybe you will output some weights for each sample, right? Each sample drawn from the prior. So in that case, you cannot use this SVT tricks, and the privacy loss will be probably not degrading with C. It will degrade with large T. So this will not be, you can really directly apply that trick that we use here. So we should think about different tricks, different methods.
Yeah, it's a good point that that if you do some form of reweighting, that you will actually use all the samples and you don't have this sparsity property anymore.
Yeah. Mm-hmm.
Let me just see if there's any other questions. There's one question about continuous time MDPs, but I'm not sure if it really relates here. So the question is, are problems discussed modeled as continuous time Markov decision processes, or in some way similar to formulations of Markov decision processes? But I think maybe the Mijung misunderstood something there in the beginning.
I guess the simulator could be microprocess, right?
That is true, yeah.
A lot of simulators for astronomy and all these things. They have a lot of like time series stuff. So maybe that's why microprocess was brought up.
Mm-hmm. And then we have another question from Babak. Let me just fully read it. Could you talk a bit more about the tightness of the bound in theory versus the experiments that you did?
Bound on, I guess, I mean, the thing is, the bound that we derived is in a sense quite loose. So improving, I was also mentioning that we still want to improve the bound. That means the bound is loose and I want to make a tighter upper bound. So in a sense, the bound we have now gives you really like worst case scenario. But that also gives us an information that your bound will decay with as we increase exponentially in n, right? So we saw this. So in practice, we also saw that as we increase n, the error went down correspondingly. So in a sense, the theory we had is reflected in the experiment, but we want to have a better theory in the end. Yeah.
I guess that's usually the problem with differential privacy, that you have a bound which might actually also be more restrictive because you try to be overcautious in a sense as well. So your bound is quite conservative usually as well. Is that true?
But I think you are talking about this bound for privacy bound, but I thought this person asked about this error bound.
Yes, that is true. That is true.
So yeah. But in sense, a differential privacy, especially the one that I used in this talk, is pure DP. So you have to have this privacy loss being bounded by epsilon for all possible outputs of algorithm and all pairs of data sets, right? So this is a very stringent concept, and people developed like a loser concept, which is called approximate DP. Now you guarantee this epsilon DP with probability 1 minus delta and so on. So you have a more relaxed version of it.
Mm-hmm. And then Siddharth asks whether you've considered other mechanisms to enforce differential privacy. So instead of, for example, using the sparse vector technique that you've been using, what would happen if you just naively added noise to the data to the observations in order to make it DP? Would that work in this case?
That could also work, but the problem is adding noise to it's usually adding noise unless you have a certain structure of your data in your data. Adding noise to the data directly is typically worse than adding noise to a function that's evaluated on the data, because data can be high dimensional, but the function value can be lower dimensional. In our case, it's just one. It's a scalar, right? So it's simpler, easier. But unfortunate side of this framework is basically you have to add noise in every iteration. On the other hand, if you add noise to the data once, then you can use it over and over again. But adding noise to the data itself typically has a very low utility because the sensitivity is really high.
Mm-hmm. Yeah, that makes a lot of sense. Cool. I think that were all the questions that the audience had. So with that, I'd like to thank you again. Unfortunately, in these virtual environments, you can only hear my claps. And yeah, so we'll now have 2 contributed talks, which are pre-recorded and where we then have a live Q&A afterwards. You're welcome to stick around for that if you want to. And I think I'll hand over to Yingzhen again to share her screen in order to show the videos. And to the audience, so you can ask live questions. And I think the speaker of the video that we're showing is actually here and can answer the question live in writing. And then afterwards, we'll also have a short Q&A where we'll answer some questions live as well. But just so that you can post some questions and then they'll get answered. And I think with that, I think we can go with the video.
Hi, I'm Hao Wu, a PhD student at Northeastern University. In this talk, I will give an introduction to our paper. Our paper is called Conjugate Energy-Based Models. This is joint work with Babak Esmaili, Michael Wick, John Trestan, and Jan-Willem van der Mint. A deep generative model is a powerful way of learning a data distribution in an unsupervised manner. It associates low-dimensional latent features with high-dimensional training exemplars in data. One commonly used class of models is variational autoencoders, aka VAEs. Many of us already know what a VAE is, but what is it for? Well, it depends on multiple purposes, and many existing lines of work interpret a VAE as a way of generating realistic examples. In this work, we have a different interpretation, which is VAE can serve as a feature encoder instead of a generator for attractive images. In other words, we'd like to do unsupervised representation learning using deep generative models. Our hope is that the encoded features can represent meaningful factors of variations, which will be useful for a broad range of downstream tasks. That's the motivation of our work. Now, let's think about this architecture more carefully. The encoder of a VAE inverts the generative model by learning a mapping from data to latent variables. Inverting means that these latent variables carry over information that is needed for reconstructing the original data. As an example, consider we train a VAE on MNIST with a Gaussian likelihood. Given the latent feature of a digit 7, the generator will map it all the way up to the pixel space for reconstructed 7. The model compares similarity by computing some exponential L2 distance. Alternatively, if it's a Bernoulli likelihood, we would compute some exponential binary cross entropy. In both cases, the quality of latent features is measured by pixel-level similarity. This can indeed be a problem when we care about learning good representations, and I will explain why in the next slide. For now, let's see how we can fix this. This measurement of similarity comes from the fact that we train a generator with the reconstruction loss. Then you would ask, do we really need a generator? Our answer is no for representation learning. So in this work, we will consider a model with an energy-based likelihood. You can think of Tx as the encoder that maps data into some intermediate space. The function eta will map the latent features into the same space. Our intuition is that we will learn more flexible densities when measuring their agreement at some intermediate level rather than all the way up to the pixel space. The reason is that with this intermediate encoding and decoding step, it becomes easier to discard useless features which are considered as noise in pixel space, while at the same time we hope to retain meaningful features. In terms of representations, it's probably a good idea to discuss what are good features and what are bad features. Consider you encode an image dataset and there is an image of an orange kitten. In the latent space, you would find its representation as well as its nearest neighbors in that space. If the corresponding images of those neighbors are also photos of cats, then the encoded features are meaningful in the sense that it puts one category of images close in that space. Unfortunately, this does not always happen. Remember I said that training a generator can be problematic? This is when good features are not necessarily learned. Because of the reconstruction loss, VAEs are sensitive to visually rich differences regardless of whether the interpretation has changed or not. As a result, VAEs consider examples that are visually similar also as close neighbors in latent space. In this example, it's very likely that VAEs give nearest neighbors that are only images of orange objects only because they are orange. And this is why we'd like to develop a new class of models as alternative to VAEs. Since we want to have an energy-based likelihood, I'll give some background on standard energy-based models, aka EBMs. An EBM defines an unnormalized density in terms of energy function Ex with an intractable normalizing constant, capital Z. We optimize the EBM by maximizing the expected log marginal likelihood. To estimate the gradient, we need samples from both data distribution and the model distribution. Since the normalizing constant is intractable, it is difficult to directly sample from the model. A commonly used strategy for generating samples is the stochastic gradient Langevin dynamics, which is what we used in training our model. Okay, now let's talk about our model. We define a latent energy-based model that is inspired by conjugate exponential family, because it has a very nice property, that is, it gets you a tractable posterior. The form of our energy function includes a natural parameters eta, a sufficient statistics Tx. Note here, we generalize the limited class of tractable exponential family by parameterizing Tx using a neural network that we optimize, naming it neural sufficient statistics. To remind you, this neural sufficient statistics serves as an intermediate level feature we discussed before. In addition, Bz is an inductive bias term that is analogous to a prior. To make use of the conjugacy, we define the bias term in form of some tractable exponential family. This allows us to factorize the joint distribution into two components. The first component corresponds to a conjugate posterior, which is in the same tractable exponential family as the bias. For this reason, we refer this class of models as conjugate energy-based models, or Cbms. The second part corresponds to an unnormalized marginal density of X. This is another convenient property because the marginal can be expressed as an energy-based likelihood. This means that we can train Cbms by maximizing the log marginal likelihood in the same way that we would train other energy-based models. Okay, we've defined a bunch of things till this point. So let's pause for a second and summarize. The common theme between Cbms and VAEs are they are both trained by maximizing a data marginal likelihood, and no supervision is needed in both cases. On the other hand, Cbms has an advantage over VAEs that it has a tractable posterior, so that you don't have to learn some inference model to make approximation, which is what VAEs require. In addition, Cbms differ from VAEs in that they lack a generator network. Although we can no longer sample from its likelihood, we can still use stochastic gradient Langevin dynamics for generation. At this cost, hopefully Cbms can learn representations that capture more factors of variations compared to Vaes. For the rest of the talk, my colleague Babak will talk about the evaluation on our model.
Thank you, Hao, and hi, everyone. What I'm going to talk about a bit is how do we actually evaluate these models? So the first natural question is, can we successfully train these models to learn the data distribution? And as my friend Hao mentioned earlier, our focus here is not generation, but to learn a good representation. That being said, we can still sample from these models and look at them as a sanity check to make sure that they in fact learn the data distribution. So here we show some generated samples from Cbms trained with a Gaussian inductive bias. And as we can see, the samples resemble examples from the data sets, and the distribution over these samples is reasonably diverse. Now that we've done with the sanity check, we come to the main question, which is how do we evaluate the latent space? In general, evaluation of representations in fully unsupervised settings is a difficult task, and in some sense it is ill-posed. And this is because what we want from a representation, or whether a factor of variation should be considered signal or noise, can depend on the downstream task. So for this work, we decided to use class labels as a proxy for this mean. So we say if your neighbor in the latent space has the same class, it's good, and otherwise it's not. But it is worth emphasizing that class label is a poor notion of similarity, but it can be helpful given that the downstream task in many cases requires knowledge about the class. So on the figure on the left, we show some samples from CFAR10 along with the top two nearest neighbor in pixel space and the top two nearest neighbor in the latent space of a VAE and a CBM. And looking a bit more closely at some of these examples, we see that pixel distance is a poor measure of similarity, which is not surprising, whereas proximity in latent space is more in agreement with class labels. So these examples are obviously cherry-picked. So to do a more thorough evaluation, what we decided to do was to encode the CFAR10 test set and classify every example based on their nearest training neighbor in latent space for each class. And looking at the diagonal of the confusion matrices, we see that the numbers for CBM is overall a bit higher, which suggests that CBM representations align more closely with class labels compared to VAEs. Now we can ask if this actually gets us anything. So we say, what if we only have a few labels available and our downstream task is classification? So here we took all the representation of different models and trained a logistic classifier using 1, 10, and 100 examples per class, as well as the full training data sets. And we compare our models against two VAs, one with a Gaussian and one with a GMM prior. Additionally, we also decided to compare our model to a standard deep EBM, where we remove the last layer and use the resulting intermediate representation as the latent code. And for CBMs, we train using two inductive biases, one with a spherical Gaussian and one with a Gaussian mixture model. And in this table, we show classification accuracies for different data sets. And we can see that CBMs overall achieve a higher accuracy compared to VAs, particularly for CFAR10 and SVHN, where pixel distance is not a good measure of similarity. And we also know that CBMs outperform the standard EBM, which suggests that the inductive biases in CBMs are in fact helpful. We hope that this work opens up opportunities for exploring conjugate energy-based models as an alternative to models that are based on VAs. And in the future, we hope to think about what are the more complex structured inductive biases that we can use and what types of application we can use these models for. And one thing we are particularly interested in is semi-supervised learning, but we think there are many other settings as well that are worth thinking about, such as disentanglement or scene decomposition, or basically anything that we would use a VAE for. And thank you so much for watching. And if you have any questions, please feel free to join our Q&A session.
Great. So that was the pre-recorded talk, which was very exciting. Thank you very much for that. And now I'm welcoming Hao and I think also Babak, the two main authors of this paper. I'll ask the audience to please submit questions. And I think while the audience still comes up with their questions, I'll get started. So you already alluded to the inductive biases of the Cbm and that they're better and in some way more suitable than, for example, a VAE or other EBMs. But I was just wondering whether you have a good intuitive understanding of what these different inductivist biases are and why they are better suited for kind of more general representation learning than, for example, the VAE.
How do you want me to take that, or?
Yeah, you can go ahead, Babak.
Okay,
yeah.
Thank you. I think in terms of so again, like what we mean by inductive biases here is so I mean, as like we pointed out, right? The GMM or the spherical Gaussian inductive bias, like these can be used in a VAE as well. So like and our emphasis here is that in Cbms we can kind of impose the same structures that we would use in other generative models. Like the important thing for us in Cbms was that you don't rely on a pixel-wise likelihood, so that the representation that you would learn in whether using a spherical Gaussian or a GMM, hopefully these clusters would actually would have an easier time, like corresponding to something more meaningful and not like something that just is like pixel based. If that answers your question.
I think partly. So I guess the question would be: is there an intuitive understanding for the inductive biases that the Cbm has, like in the structure of the loss function, for example? Because you say you compute the loss in this intermediate space, basically. And I'm just wondering what is whether there's an interpretation to this intermediate space or the type of loss that you have there that make it better suited than pixel loss.
Right. So we are actually currently working on it, and so it turns out that given that every exponential family there's a bijection to Bregman divergence, it turns out that you can actually maybe explain this the generative model of VAE and a Cbm in terms of Bregman divergence. So roughly speaking, in a VAE, the Bregman divergence happens at pixel space. So as in we transform Z with a generator to the same space as X, and we kind of measure a Bregman divergence between basically the reconstruction and the original image, while in a Cbm, and this Bregman divergence happens at the latent space. So it happens basically between the natural parameters of Z and a lower dimensional X, which is like the neural sufficient statistics. So whether this is actually whether like how insightful this is, we're still like kind of thinking about it a bit more. But overall, we at least feel like that because this Bregman divergence happens at latent space, if we kind of can at least hope to like learn something more meaningful in that sense.
Yeah, that makes a lot of sense. I'm looking forward to seeing that analysis.
Right.
And there's a question from Ying Zhen. So in exponential families, we actually have quite a large number of inference methods that have been developed over the years. And the question is, can these kind of more elaborate inference methods for exponential families be applied in this setting? And how would you imagine doing this?
I think so. In this work, we try to do inference based on the fact that we assume a conjugate prior to the likelihood, so that we have a tractable posterior. In the sense that there's no need for us to approximate the posterior by learning some inference model. But I think there's definitely chances to try the existing inference methods to see if it can solve this type of energy-based model better. Does that make sense?
So I'm waiting if, yeah, Yingzhen is very happy with the answer.
Cool.
Then Alexander asks, how do the lambda tildes compare to the expected sufficient statistics? Is it trying to learn the conjugate prior natural parameters that generate have a mean of t of x, and what would any bias from that mean? Not sure. I think there were a couple of words in there, but yeah.
Right. So the term tilde lambda is defined in the posterior. Is defined with the lambda from the inductive bias with an additive term that is the sum of the neural sufficient statistics, which is which is when you have a closed form conjugacy relationship, you would also have the same form of a parameter for the conjugate posterior. So we just got intuition from the analytic form and try to mimic that form of conjugate posterior, but with parameterizing the sufficient statistics with some neural network and try to learn that, yeah, as an encoder. And what's the other?
Just to add to that, yeah, for the spherical Gaussian, we actually learned we fixed the lambdas there, so it was that so that it corresponds to like zero mean and like one standard Gaussian. For the mixture model one, that there actually we started learning the lambdas as well, so that the mixtures could move away. As for the exact agreement with t versus lambdas, we didn't explicitly look at this. We kind of just the main evaluation we did was just computing the mean of the posterior for every example, and then like we try to like visualize the latent space to see if it's separate enough, but yeah, that I need to think about a bit more personally. So yeah, thanks for the question. Yeah.
And then maybe as the last questions about the origin of EBMs and what does high and low energy mean intuitively for someone who's not familiar with these models?
Yeah, so this type of energy-based model is originated from physics, and it has a long history. So previously, people have been studying what is called restricted Boltzmann machine, where or RBM. So in the RBM, there's usually one linear layer where the hidden units and the observed values are binary valued. So more recently, people have been thinking of this energy-based model, which are parameterized by deep neural network, and specifically working on image data set and also language models to see whether we can revisit this type of models and try to figure out some kind of answers from that.
Perfect. Okay, I think we're out of time, so I think we'll switch to the next talk. Thank you very much, Hao and Babak, and very great work.
Thank you very much.
Presenting.
Yeah. Thank you very much. Yeah.
Great, and so yeah.
Hi, I'm Will Tebbutt. I'm a PhD student at the University of Cambridge. This talk is about some recent work I've been doing with Onno Solin at Aalto University and my supervisor, Rich Turner, which looks at a way of combining two classes of approximations for Gaussian processes applied to spatiotemporal problems. So I'm interested in spatiotemporal problems because they're everywhere. I'm particularly interested in them in climate science. And I'm interested in GPs because I think that they're probably good candidate models for a lot of the phenomena that the spatiotemporal data we have describes. So at the very least, I'd like to be able to try them out. But of course, spatiotemporal data sets can be quite large, and GPs famously have scaling issues. So there are lots and lots of types of approximations for GPs. The two that we consider in this work turn out to have really complementary strengths. So the pseudo-point approximations, which are probably the most famous within the machine learning literature, are really good at space. So lots of points in space is fine. But they're bad at kind of long time series problems. They really break down in that context. Conversely, state space approximations are really, really good at long time series problems. They scale linearly there. But they struggle with large spatial domains, and they don't work at all if the observations you get at every time point change where they're located. So it's natural to ask, could we combine these two things to get the best of both worlds and kind of deal with some of the issues that these things have? And the answer turns out to be yes for certain classes of GPs. And that's what we show in this work. So we can combine them, get the best of both worlds, deal with the time issues, the scaling and time issues of pseudo-points, the spatial issues of the state space approximations, and some of the results are really clean as well. We get analogues of kind of standard pseudo-point approximations, but in the spatiotemporal case. And I'll expand on what I mean by that in this talk. So the first ingredient, pseudo-point approximations. The gist is you want to do inference in a GP. You've got a lot of observations. Maybe you don't need that many observations to describe the posterior. Maybe you could just kind of pick some carefully chosen fake pseudo observations, use the prior from your GP and those pseudo observations to induce a simpler process, or simpler to describe process, and use that to approximate your posterior. And indeed, this is what the kind of standard pseudo-point approximation does. And so it does standard variation inference. It minimizes the KL divergence between the approximate process induced by the pseudo-points and the exact posterior. So the second ingredient are the state space approximations. The one way of looking at these is you take your original process, you augment it with some additional processes, and the thing you get out looks a lot like a multi-output GP. And when you do this, well, you do it in such a way that you get a Markov property through time. And once you've got this Markov property, you can do inference very efficiently in linear time. The third ingredient is separable kernels and sums of separable kernels. So Antonio Hagen showed in 1998 that you can, if you have a separable kernel, so in this case it's kind of space-time separable kernel where the kernel over space and time is a product of a kernel over space and a kernel over time, that there's this conditional independence property, which is definitely most easily interpreted graphically. So all it says is that the process at the blue square is conditionally independent of the process at the empty red square, given the process at the black circle. Now, I personally found this property quite surprising. I don't know how well it's known. And it's quite straightforward to show that this extends to collections of points and multiple collections of points kind of through time at different points in space. And so this property motivates kind of the following idea. So if we were to take a state space approximation and with a separable or some separable GPs, and construct a pseudo-point approximation to that, put the pseudo-points on a grid, then the prior, given that you've made the state space approximation over these pseudo-points, would be Markov through time. And indeed, that's what we do in this work. And this frees you up to make observations anywhere you like in space, provided that the only constraint there being that you have to have, at any time that you have an observation, you must also have a full set of pseudo points. And so once you do this, you wind up with the result that the optimal Gaussian approximation to the posterior is Markov, which is equivalent to saying that the precision matrix of the optimal Gaussian approximate posterior is block tridiagonal. And the reason that this happens is because the prior precision over the pseudo points, lambda u bar, is itself block tridiagonal. And the optimal approximate posterior precision is just the sum of that and some factors associated with the observations you made. And because the data points at time t only affect the pseudo points at time t, because of this conditional independence property, this matrix that you add on is itself block diagonal. So when you add a block tridiagonal matrix to a block diagonal matrix, you get another block tridiagonal matrix, which is this optimal approximate posterior precision here. Now the upshot of this in terms of complexity is that rather than the naive total number of pseudo points squared times total number of observations complexity, to say compute the elbow, the cost of computing the elbow is now only the total number of time points times the number of pseudo points squared per time point times the number of observations per time point, which is a very, very significant reduction. And kind of, I guess the key point here is that this now scales linearly in the number of time points, which is not the case for pseudo point approximations. As you increase the number of time points, you typically have to add more pseudo points, which means that you're not linear in the number of observations. There are a couple of other nice kind of points with this. So it turns out you can implement approximate inference as exact inference in an approximate model, which is great from a code reuse perspective. And this, in the paper, we show that some earlier work combining these two classes of approximations, it was kind of FITC inspired, but we can show that it's actually doing FITC in the state space approximation. I don't believe that was apparent at the time. So we've got some preliminary timing experiments just to show that this kind of works as expected. So the first one looks at if you've got a grid of observations just with a few missing data, which is a situation that the kind of standard state space approximations can handle. We see performance improvements in terms of the time to compute the log marginal likelihood or the elbow for the pseudo point approximations, and the most expensive pseudo point approximation here, the elbow is very, very close to the log marginal likelihood, so it's providing a good approximation. And we see similar results in the case where the observations come in at completely arbitrary points in space, at every point in time. And of course, the state space approximations aren't applicable here. So to summarize, there are 4 ingredients to this: state space approximation, form a pseudo point approximation to that state space approximation, restrict your kernel a little bit, grid your pseudo point locations, and you can get an efficient and accurate approximate inference scheme for kind of spatial temporal GPs that deals with some of the issues of pseudo points and state space approximations.
Great, thank you very much for the talk and the great video. And now we have Will here live to answer any questions. And I think in the Q&A so far we have one question, although I think it might still relate to the previous talk, unless you can make sense of it in this case, which is asking about the neural ODE point of view, and I think that still relates to the energy-based models. So I'll ask that was for the previous one. If there's any other questions, please post them. And otherwise, I'll have a couple of questions. So the first would be, how restrictive is the assumption of a sum-separable kernel in this setting?
Right, yeah, so it is a restriction, definitely. So separable kernels in particular are quite restricted. So they can't tend to represent things where you have kind of, if you imagine a process that varies very slowly in time and space, has like one length in time and space, but also has like kind of a fairly quickly varying bit in time and space, and you kind of then a separable kernel can't really handle that. It kind of has to be both. It either has to be slowly varying in like in time and space, or quickly varying in time and space. It kind of can't be both at the same time. But sums of these things can be. So that's a bit less restrictive. It's not clear to me like the exact extent of or how important this is in practice. Like lots of the spatiotemporal GPs use separable kernels, I think largely because of tractability reasons. Mm-hmm. They just tend to have nice properties.
Yeah.
But I like certainly if you just wanted to like use like your favorite kernel for a spatiotemporal problem, then this might prevent you from doing that.
Mm-hmm. That makes a lot of sense. And then maybe a second technical question would be, okay, there's a live question now by Mayank. Are there any extensions of adding sparse kernels here?
I'm not quite sure what's meant by a sparse kernel here. Maybe this is one that's got a sparse precision structure, or
maybe Mayank can clarify in the chat briefly what he means. Yes, so it's about the sparse structure, like this, as you mentioned.
Yeah, so I guess if you had like a graph kernel or something where you've got a sparsely connected graph. Yeah, so what I didn't discuss here, of course, is that there's no real restriction on the type, on what you call space. So here I kind of suggested it would be some kind of like, low dimensional Euclidean space, but it doesn't have to be. So it could be that you have a graph, like a spatiotemporal graph, so a graph that evolves through time, where you've got, say, a fixed topology for your graph, and you've just got a value at each node on your graph. That would be totally fine. And then in that context, it really just looks like applying a standard pseudo-point approximation to a graph. So that should be fine.
Yeah.
But you still have this separable structure over space and time, of course.
Mm-hmm. So you showed these simple timing experiments. I was wondering in the beginning you motivated this with the climate science example, and I was just wondering if you actually managed to apply this yet, or whether this is still ongoing work.
Yeah, so it's ongoing. I'm looking at some temperature related problems. I spent time looking at how to kind of combine the outputs of multiple climate simulators as well. So that's kind of where I'm going with this.
Mm-hmm.
But yeah.
Oh, this is very exciting work. Looking forward to that. So I think there are no further questions, and we're already running a bit over time. So thank you very much, Will, for joining us and for presenting your work. And with this, we're almost closing. So I just want to announce that in the next session, which will also be the last session of our series, which will take place at the usual time of 5 p.m. GMT and 9 a.m. Pacific time, we'll have an invited talk by Yasha Sol-Dickstein from Google Brain on infinite width Bayesian neural networks, which should be very exciting. And then 2 contributor talks, one by Matt Hoffman about round of errors in Metropolis Hastings accept reject steps, and one by Alex Alemi about VIB is half Bayes, which should be very exciting. So I look forward to seeing you all, and wish you a good day or good afternoon, good evening, wherever you are. Thank you very much for tuning in. Bye-bye.